So for long run behavior, and again, just as a reminder, this can also be called end behavior or global behavior. These are all accepted terms. Behavior. This is coming from the leading coefficient of our polynomial. So whenever we want to describe our long run behavior, we're going to need to find that leading coefficient first. Because coefficient. Okay, so that leading coefficient is going to give us the general shape of our graph. Again, with the long run behavior, we're just focusing on what's happening at the ends of our graph, so what's happening out at the infinities. And again, our general structure, we're going to say like as x approaches negative infinity, f of x approaches, and then we need to find that last piece. And then we also need to look as x approaches positive infinity, f of x approaches, in finding that last piece there. So let's go through a few examples with this, and we'll look at the graphs to see how this is working out. So we're going to identify the leading term, graph the function using technology, and describe the long run behavior. But actually, I'm even going to skip that graphing the function using technology. I'm not going to skip it, but I'm going to save that for the end, because I'm going to show you how you can find that long run behavior without the graph. So this first function here, first thing I need to do is finding the leading term. Now, leading term only occurs when it's in standard form, meaning our exponents are decreasing left to right. So 3 is not our leading term here. To find our leading term, I'm going to look for the highest degree term, or which term has the largest exponent, and that's going to be our positive x cubed. So the leading term is just positive x cubed. And I would want to include any number, or if it's negative, that would all be very important. This is just positive 1, so this is just x cubed. Now, what we're going to need to keep in mind here is the general shapes of our power functions that we talked about. So let me see, did I leave myself any room? Yeah. Okay, so if it's an even power, then we're going to expect kind of this parabola-like shape, either up or down, depending on if our leading coefficient is positive or negative. If it's an odd power function, our general shape is like our cubic function, so coming from negative infinity going off to positive, or positive infinity to negative infinity, and that's going to depend on our leading coefficient being positive or negative. So with our leading term here being x cubed, what I'm going to do is just draw a little shape next to it, and since it's positive 1, it would come from negative infinity and go off to positive infinity. So that little sketch actually shows me my long run behavior of the graph. So this is where I will go to technology in a second, but I can go ahead and write the long run behavior just based on that little sketch right there. So for the long run behavior, as x goes to negative infinity, f of x goes to, so what I'm thinking about is as I move to the left here, where do the outputs go? And the outputs are going down, down, down to negative infinity. As x approaches positive infinity, f of x approaches. So now I'm thinking as I move to the right along the x-axis, and we can see our functions going up and up and up and up towards positive infinity. So with that, I have my leading term, and that leading term had me answer my long run behavior, but now let's check it with the actual graph of this entire function, because there's so much more going on with this function. But in terms of long run behavior, all we're worried about are the little arrows on the end there. So I have my function here, and as you can see, there's more twists and turns in the middle, but that's our short run behavior or a local behavior. So with that, we're not worried about that right now. We're just worried about what's happening at the ends here. And as we can see, we're coming from negative infinity and going off to positive infinity. So that's where this little sketch right here is really all we need to answer that long run behavior, since we're not asking questions about what's happening in the middle. All right, let's go through the same steps here. Now this is a little different, and this is called the factored form of a polynomial, since we can see all of those nice factors in there. Factored form. So the leading term, this will have a little work to it because with it being all factored out, we can't really see our leading term right now. Now, if you're worried that I'm going to start foiling all of this out, don't worry, we're not going to. We want to be very a bit lazy with our math here. But the idea is that our leading term is all about x and getting this highest degree on x. So what would happen is if we did start foiling this out piece by piece by piece, what's going to make up the leading term is multiplying all of the pieces that have x involved with it. So what I'm going to focus on is, okay, I need this whole negative 2x outside, because as we could think of like just multiplying these first two pieces, that would distribute in, but really I'm just worried about how that would multiply with x. And then whatever I got there, I would be looking at how this term then foiled into here or distributed, and then we'd see how our degree would grow once it multiplied with that x, and multiplied with that x, and multiplied with that x. So this leading term, we don't have to multiply all of it out. What we could do is just grab these values with x and multiply them together. So this is going to come from negative 2x times x times x times x times x, which is going to be negative 2 times x to the 1, 2, 3, 4, 5. So when you have the factored form, you can find the leading term in this way, and you don't have to multiply all of it out. Just focus on the pieces where x would be multiplying with itself, because that's what's going to be bumping up the degree. Now, when we have just x to the 5th, then we would have a shape like our cubic function. However, we have a negative symbol out front, so where our odd functions typically go from negative infinity to positive, this reverses it, and we would have coming from positive infinity going off to negative infinity. So for a general shape of my graph, seeing something like that. So to answer the long run behavior, what we'll have is as x goes to negative infinity, f of x goes to, and so as we move to the left here, so as we go in this direction to the left-hand side, our function is going up and up and up and up towards positive infinity. And as x goes to the right, so as it goes towards positive infinity, f of x is going to be going in a downward direction, which means that's going towards negative infinity. And just to check this with the graph itself, I'm going to get rid of that one and show this graph, which we can see there's this whole mess of stuff happening in the middle, but we're not really interested in that. So I'm just going to scroll out until it looks a little clearer. This is a little tough to see. I could adjust, in fact, let me go ahead and stretch out that x-axis. Let's go negative 50 to positive 50. All right, there's a better visual. So as we can see, we're coming from positive infinity, and then stuff happens, and then we go off to negative infinity. So with that, our picture matches, and we have our long run behavior to go with it. All right, this function here, looking for the leading term. So this is not factored form, so I can just do the straight look for the highest exponent. So that's coming from that x to the 4th. So I want to focus on this whole negative 1/4 x to the 4th. So the leading term is this negative 1/4 x to the 4th. And something I didn't mention up here with the 2, and I'll talk about it here with the 1/4, that numerical value, as we talked about, that would be causing our vertical stretch or compression. And that's really focused on our short run behavior, kind of these specific points where here we're just looking out at the tail ends of our data, or our, not data, but our function. So with that, this number itself doesn't particularly matter right now. It being positive or negative absolutely matters. So with that, even though we're including this number, I'm not thinking about that 1/4 so much, but I am thinking about the fact that it's negative. So we have an even power function, which often looks like an upwards parabola. However, it's negative, so that's going to make it an opening downward parabola. So with this function, what I can see is on both sides of the graph, we're going off to negative infinity. So it doesn't matter if x is getting smaller or x is getting larger, no matter what, our function's going to negative infinity. So for long run behavior, we're going to have, as x goes to negative infinity, our function is going downward towards negative infinity, and it's going to be the same on the other side as well. As x goes to positive infinity, our function is going down towards negative infinity. So if we check this with the graph, we can see our function's down here, and it goes to negative infinity, negative infinity. Again, there's some cool stuff happening in the middle there, but that's our short run behavior, which we'll talk about later. All right, our last one here. So our leading term is that positive 12x squared, since that has the highest exponent. And with this, so x squared would give us a parabola. Again, that numerical value of 12, I'm not really worried about right now. I'm just going to use the fact that it's positive. So since it's positive x squared, that means we'll have an upwards parabola. So for the long run behavior, we have both sides of the function going off to positive infinity. So I'm going to say as x goes to negative infinity, f of x goes off to positive infinity, so it's going up. And as x goes to positive infinity, so as we move to the right, our function values are going off to positive infinity since it's going up. All right, so in short, with our long run behavior, let me just make a little side note here. So for long run behavior, look at the leading term. So find that leading term, which is an x to the power of n, and the long run behavior follows the power function that an xn. So even though we have other terms adding and subtracting onto it, those terms are determining the short run behavior. It's going to just be this leading term that we focus on for the long run behavior.